Okay, YouTube, up until now we've been exploring the quadratic formula in this last module, and now that we've kind of practiced this quite a bit, we're really well equipped to deal with some application type situations in which we're going to have values that are, pretty maybe exotic. They're not very nice integer values. And so what I'm going to do is I'm going to introduce what we call projectile motion, a formula for projectile motion, and then we're going to use the quadratic formula to kind of help us solve for some values that we care to find. So let's start with this. We say modeling projectiles using parabolas. Of course, if I were to tell you that when I shoot something into the air, I could tell you that I could model time on the x-axis, and then I could tell you the height of this object at any given time. Basically though, if I told you this, and also that it followed a parabolic path, I don't think it would be that much of a shocker. As a matter of fact, things that go up tend to come down, and they go up slower and slower, and more slowly, and they start to come down more and more quickly as they fall more and more. So knowing this, actually what I have to tell you is that the path of a projectile in motion actually follows directly a path of a parabola here. So we can model this using what's called the position function, okay? And basically we say we can model mathematically the height of a projectile, so I put height here, in feet at any given time in seconds using this position function. We say the function is usually presented in two forms. So we say where v sub 0 is the initial velocity, okay? So one thing I want to point out here is this. We use v for velocity, of course, but we use v sub 0 to indicate that that's the velocity at time 0. And we use h sub 0 here to indicate the initial height of the projectile. So v sub 0, initial velocity, initial height is h sub 0. So the two different forms of this equation are given thusly. And the first one is for when we drop an object. The second is for when we launch or throw an object, okay? So this first one here, you're going to notice that our height, or h of t is what we should really call it, is equal to negative 16t squared plus h sub 0, where this h sub 0, again, is the initial height. And I'm going to put an arrow here. We say this is the initial height when the experiment starts, okay? So this formula is a little bit different than our second formula here where we launch or throw, because you'll notice that our h of t is given as negative 16t squared. We still have this plus h sub 0 at the end, but you'll notice that there's plus this v sub 0 t, or in other words, the initial velocity times time to the first power in the middle here. So the reason why we neglect putting that term all together in this first instance here is because when we drop an object, what I want you to understand is that the initial velocity is we're neither throwing it up nor are we throwing it downward, we're just letting it go. Then we would assume that the initial velocity is actually equal to 0. And if that's the case, 0 times t would cause that term to drop out altogether. So the form of this position function that I really want to get used to is actually the second form. So our height at any given time in feet and in seconds is negative 16t squared plus initial velocity times time plus initial height. So very quickly, before we get into applying this in an example, I want you to understand that initial velocity, the direction of that initial velocity, actually makes a difference here in terms of its sign, S-I-G-N, sign. So we say, as shown, the value of v sub 0 can be positive, negative, or 0 depending upon whether the object is launched upward, downward, or parallel to the ground. So what you'll see here is in this example where this gentleman's golfing here, because he's putting an initial force upward on this ball here, we would say that his initial velocity would be considered to be positive, whereas this young lady is spiking a volleyball downward, her initial velocity would be said to be 0. So maybe their initial velocities are the same. Maybe it's 50 feet per second here and 50 feet per second here. But I want you to understand that we would call this positive 50 feet per second or positive 50, whereas we'd call this negative 50. And then, of course, you notice this says, or if it's parallel to the ground or you're not imparting a force altogether on this, then we say the initial velocity is said to be 0. And that would be like the case where you're dropping it here, okay? So let's look at our example here. It says a juggler tosses a ball into the air. The ball leaves the juggler's hand 4 feet above the ground and has an initial velocity of 40 feet per second. So it says the juggler catches the ball when it falls back to a height of 3 feet. What we want to do is use this model to find how long the ball is in the air. So let's start with our model here. Now, the things that I want to point out are the values that we need really are the initial velocity and the initial height, which we had those up here. We said 4 feet above the ground and 40 feet per second. So our initial model is the height at any given time t can be modeled by negative 16t squared, which was a given in this formula, plus in this case 40t, because our initial velocity is 40 feet per second, and then I'm going to say plus 4 because our initial height is 4. So this model right here, as a matter of fact, if we were to plug in a time t, say 1 second, we could actually solve and tell you how many feet off the ground it is at that time, which is a pretty profound thing. So again, recall that we have time and then height at that time of our parabola. It looks like this here, something that's modeling. That's not very good here. Let me get that out of here. Here's more of a parabolic arc. Here's our projectile that we're looking at right here. So what we're looking at is this. We want to find how long the ball is in the air. In other words, look for the time. So the question we're trying to answer is how long is the time, but for what is the height? You know, what is the height that we're given here? So we must have been given a height to go plug in for height to solve backwards for time, and that's what this 3 feet is here. So basically what we're going to do is we're going to substitute that 3 feet in for the height and say how long would it take our ball to reach that height of 3 feet. And so the neat thing about this is because we have the quadratic formula now, I can actually just set this equal to 0 by subtracting the 3 back over the right side. We have negative 16t squared plus 40t plus 4 minus 3, which is plus 1. And so immediately what I'm going to run and do is I'm going to identify a, b, and c, and then we're just going to drop these into the quadratic formula here. So we have negative 16, 40, and then positive 1 respectively for these values. And instead of using an x this time, I'm going to use t for time. We get negative b plus or minus the square root of, we'd have b squared minus 4 times a times c. And this is all over 2 times a. So now looking at this, we would say, well, our b value is 40. We're going to drop that in there and there. Our a value happens to be a negative 16, so we get negative 16 and negative 16. And then our c value conveniently is 1 here. So simplifying this, as we usually do, we say negative 40 plus or minus the square root of something. And this is all over 2 times a negative 16, which is a negative 32. So let's think this out here. We say 4 times 4 is 16, so 40 times 40 must be 1600. And then I have a negative times a positive. So this whole value here will be positive. It looks like 4 times 64, we get 64. So our two solutions in this case are going to be negative 40 plus or minus the square root of 1664. And this is all over negative 32. So in order to find our 2 times, I'm going to say approximately equal to here. It's supposed to be squiggly, squiggly, squiggly. There we go. And I'm just going to get my calculator out here, and I'll turn this on, clear these out. On, clear. So we're going to type this in, all of this expression right here, starting with everything on top being in parentheses. So we say negative 40. We're going to go with a positive first, plus the square root of. So you notice the square root of, when I hit this, starts a new parenthesis, and that's going to trap that 1664. End parenthesis. Now this last parenthesis traps everything that's on the top of this expression. And we're going to divide that all by a negative 32. And so I get this value here, which is a negative time, which is an interesting thing in and of itself. And then I'm going to hit second enter to pop up the last thing I typed in. And I'm just going to go back up here. I'm going to scroll up here, and I'm going to change that plus to a minus. And we're going to evaluate this again. So we have both at negative 0.02 and about 2.52. So we say negative 0.02 seconds. We were solving for a time here. And then we have 2.52 seconds. So the weird thing about this is in the context of this problem, that negative time is not something that is reasonable. So to answer this question, when does it get back to a height of 3 feet or get to a height of 3 feet, it's going to be about 2.52 seconds later. And to solve for this, all we had to do is plug in the height and go backwards and solve for the time, which is really convenient to do using the quadratic formula. So now what I'd like to do is this. I want to find the maximum height of the ball and the time at which that height occurs. So knowing that our maximum height, since this opens up downward, must occur at this vertex value, we're basically going to be solving for where the vertex is. What I want to point out is that this is really the time and then the height of that time at that time. And because we have an equation that is in standard form, we need to recall that in order to find the vertex values, we really have negative b over 2a, and then the function value that we're going to get when we plug that negative b over 2a into the function. So let's start with this. The time, or the axis of symmetry value here, the time at which it reaches its maximum height is actually the thing we're going to solve for first. We'd have negative b over 2 times a, where our b value is 40 here, and then our a value is a negative 16. So we really get this, we get negative 40 over negative 32, which comes out to be some decimal value that I'm going to find here. We're going to say 40 divided by 32. So what I know is at 1.25 seconds, okay, this is the time at which it reaches its maximum height. Time at max height. So it takes the ball that long just to reach its maximum height. Now in order to find that maximum height, all we're going to do is say, well, then I need to actually plug that into our function, that time into our function. And so what we're going to get here is this. We're going to get h of 1.25, which plugging this in, we get negative 16 times 1.25 squared, plus 40, which was our initial velocity, times the 1.25, plus 4, which was our initial height. So using this calculator, we can actually just type this in as we see it, and we're going to say, well, then we would get negative 16, and then times in parentheses 1.25 squared, plus now 40 times in parentheses 1.25, and then we'll say plus our initial height of 4. And what we can determine is that the maximum height of this ball, or this projectile in this case, occurs at 1.25 seconds into its projectile motion here, and it happens to be 29 feet into the air. So that's our projectile motion formula, or position function, and how we can use a quadratic formula to help us out here.